All right, so compound probability, word compound, you are correct, means multiple things happening, okay? A compound event, okay, and remember the event is the scenario that we're interested in occurring, is an event composed of more than one event. Okay, it's like compound word. Compound word is a word made up of multiple words, right? Okay. Compound fraction, a fraction made up of multiple fractions. Well, we've seen that word compound before. So compound probability can be found by analyzing the probability of each event within the compound event. Okay, so what that means is that if I ask you what's the probability of rolling a dice, getting a 2 and rolling it again and getting a 3, okay, that probability can be found by analyzing rolling the dice the first time and then rolling the dice a second time and looking at them as individual scenarios. Does that make sense? Okay. Now, there are two types of events that we're interested in. And the types of events that we're interested in are going to dictate the approaches, the formulas, and procedures that we go through to determine probabilities. Okay? The two types are what we call independent and dependent. What is the difference? What do those words mean, Jagger? Okay, so independent, the two events or three events, however many there are separate from one another. Okay, meaning that if I want to roll a dice and flip a coin, whether I get a 6 on the dice has no bearing, has no impact or reliance on the fact that maybe I get a head when I flip the coin. Does that make sense? So those are independent events. When we start talking about using probability in real life, we like to set up studies of like medical studies on working with like new medicines, new drugs, okay? And we do trials. And what we do is basically say, okay, we need to put a group of people in a placebo group or a control group, and we need to put somebody in a treatment group. And we keep them away from each other. You can't be in both groups at the same time, okay? And it creates that independence. So if the result of one event does not affect or impact another event, then the event is said to be independent. If the result of the event has some impact on a second event, then the events are said to be dependent, okay? We'll go through some scenarios here, verbal scenarios that we can realize, okay, there is a relationship between these two, okay? But there is also some algebraic formulas that we'll run through that if provided just the data, we can decide whether two events were independent or dependent as well, okay? So here are some examples. It says, are the outcomes of each trial independent or dependent events, okay? So it says choose a number tile from 12 tiles, then spin a spinner. Okay? Is that independent or dependent? Those are independent. Okay? The fact that I choose a tile that has a number 7 on it has no bearing on whether I spin the spinner and it lands on the color green or something like that. Okay? So those would be independent. If I pick one card from a set of, say, 15 sequentially numbered cards. So that means they start at 1 and go to 2, go to 3, go to 4. Pick one of those cards. Then without replacing it, so I take that card, I pick one card, put it in my pocket. Then I pick another card. Okay, so the scenario here is, let's say we got cards 1 through 15. And I want to know what is the probability that you, on your second, you pick a card, put it in your pocket. On your second pick, you pick a 3. Why is it dependent? Right, so it depends on, maybe that 3 was the first one I chose, right? So in the second choice, it's not in there anymore. So that probability would be 0. But maybe that 3 is still in that set of cards. But when I kept that card and put it in my pocket, now the sample space changed for the second selection, right? Okay. One way that I usually look and try to decipher if events are dependent or independent is in that second event, did the sample space change? Okay. Generally, if the sample space changes, then you most likely have dependence. Okay. So when we talk about so a lot of questions you'll go with, or you'll see or come across, will be choosing marbles out of a bag, choosing names out of a hat, picking cards. They use those scenarios, and they're really all the same scenario. Okay, but they use those three structures, and they'll use the words with replacement or without replacement. If they say with replacement, then they're independent events. If they say without replacement, so you're keeping it, and you're going to then maybe choose another marble or choose another card after keeping the first one, then you're going to have dependent events. Okay, so with and without replacement are keywords to look for. So if you roll a standard number cube, then you flip a coin. Are the outcomes independent or dependent? Independent. Okay, my outcome on the number cube or the dice has no bearing on heads or tails on that coin. Okay, so you can find the probability that two independent events will occur by multiplying the probabilities of each event. Okay, so I'll zoom in on this key concept here. It says the probability says if A and B are independent events, then the probability of A and B occurring is the probability of A times the probability of B. And there's some different notation that we're going to go through here in a moment. Instead of using the word and, that usually the end of course exam uses. We use it heavily in statistics classes. We like to take the word and out. We don't like to have essentially words in our formulas. All right, so if we've got two independent events, we say the probability of A and B occurring, that in a different notation. And you may have seen this last year when you did like inequalities. Have you guys ever seen this symbol? That symbol right there? Okay. In inequalities, that refers to the word intersection. It still means intersection here as well, but it's both things happening. Okay. So when we did intersection, we did like if I gave you a number line and I said, let's say 3, we did like greater than or equal to 3, so we drew that. And then I gave you another number line starting at, like, let's just say 0, and I graphed it like that. And I asked you, let's call this A and this B. And I said, what does A intersect B? You would tell me it's where they both are occurring at the same time. Does that make sense? Okay, so that occurring at the same time is the same logic that we're using here in probability that we learned when we talked about inequalities. Okay, so the word and right there replaced with that symbol. Okay, still interpreted the same way. So then this would be P of A, then times P of B. And that is our formula of two independent events. Okay. If you have two probabilities, okay, of event A and a probability of event B, multiply them together will tell you exactly the probability of them both occurring either simultaneously or consecutively. We've got some other formulas that we'll talk about with independent events as we move forward through the rest of the course or the lesson today, but that's the main one. Okay. So here it says so every time that we do a problem, and this is something that you just have to kind of beat into your head every time you see a probability question. And we still talk about this in my stats class every single day. When you read a question, the number one most important thing is to decipher whether the situation or scenario that's occurring has independent or dependent events occurring, okay? Because that's going to guide you down different pathways for different formulas, okay? So that's the first thing that we're interested in. So the desk drawer contains 5 red pens, 6 blue pens, 3 black pens, 24 silver paper clips, 16 white paper clips. It says if you select a pen and a paper clip from the drawer without looking, what is the probability to select a blue pen and a white paper clip? Okay. Now, here's my question. Does the fact that I pick a blue pen, does that impact the amount of paper clips that are left over? No. Okay. The fact that I pick a white paper clip, does that have any impact on how many pens are left over? No. Okay. So the selection of a pen does not impact the selection of paper clips and vice versa. So these are independent events. Okay. So the way I'm going to write this, I'm interested in the probability. Okay. I'm just going to say BP for blue pen intersect WP for white paperclip. Okay. Because we're able to identify them as independent events, then we know that the probability of both of them occurring, okay, blue pen and a white paperclip, is now the probability of a blue pen times the probability of a white paperclip. Let's actually call this, just so we don't get confused later on if we have to come back and look at this, let's just say WC for white clip, so we don't get the P confused with paper clip or pen. So blue pen intersect white clip, paper clip. So what is the probability that we get a blue pen? Well, now this is our classic probability. How many blue pens are there? 6. So those are our favorable outcomes. Divided by how many pens are there, the total number of outcomes, 14 total outcomes. Okay. I'll multiply that then by the probability of a white paperclip. How many white paperclips are there? How many total paperclips could I have chosen from? Okay. So now you could do some reduction, might make it a little bit easier. I see a 2 in here, and I'm going to put the 2 out of this as well. Can you see a 4 in there and a 4 in here? Can you see then a 2 in there and a 2 in there? Does that kind of make sense? So you get 6 over 35 after doing that cancellation, which I think is easier than multiplying 6 times 16 and 14 times 40 and then trying to see what cancels out of those products. 6 out of 35. So what we're saying, and this is our understanding of this collective probability at the end. We're saying 6 out of 35 is our probability. We change that to a decimal. 6 out of 35 is a decimal. It's 17%. Okay, 17%. And you can think about it, if I take 35 times 3, that gives me what, 105? Okay, so 6 times 3 gives me 18. So 18 out of 105 is almost like 18 out of 100, right? So we can maybe estimate that way, but we get 17% as our probability there. What that means to us, okay, if I view it as 6 over 35, it means if I were to conduct this experiment 35 times, have my desk arranged like this, close my eyes, pick with my left hand a pen, my right hand a paperclip, 6 out of those 35 times, I can expect to get a blue pen and a white paperclip. Does that make sense? That's what this is theoretical probability here. That's what we can expect. Okay. Now, if we do that 35 times, we might not get 6, but we'll probably get something close to that. Okay. The experimental probability might be a little bit different. The 17% as a decimal says the same exact thing, but instead of doing it 35 times, the idea of it as a percentage is if I were to do it 100 times, I'm going to get, of those 100 times, 17 of those times, I'm going to get the blue pen and a white paperclip. Does that make sense? Okay. So 17 out of 100 is kind of the, or let's say 6 out of 35 is the simplified version of 17 out of 100, essentially, when we look at it that way. Is that cool? Can we do that? So you roll a standard number cube and spin the spinner at the right. It's probability to roll a number less than 3 and the spinner lands on a vowel. Okay? So we're going to go probability of less than 3 and vowel. Okay. That then, so if we're using notation, and this is all stuff that you would have to maybe decide on your own, and it's not consistent across probability. You know, if you want to say, and maybe we go less than 3 that way, and V for vowel, if you want to be more concise with how we're going to write this instead of using all those words, doesn't matter. But if I roll a dice, does that dice have any impact on whether I spin this and it land on a vowel? No. Okay. So this is going to be the probability that we are less than 3 times the probability of a vowel. What's the probability that you get a number that is less than 3? Okay, so 2 out of 6. So 1 and 2, right? Why didn't I choose 3? Okay, so 2 out of 6, which reduces to 1/3, right? Okay. And we're going to multiply that probability of vowel. How many of these letters over here are vowels? 1. So we get 1/4. So we get 1/3 times 1/4, which ends up being 1/12. So the argument then is if I do this 12 times, only one of those 12 times will I get a number that is less than 3, and I land on the U. Does that make sense? Okay. I mean, you could, in this situation, because the sample space is going to be small, let's see if we can construct the sample space here. We could have, so let's say we spin the spinner, we could have a U, a V, a W, or an X, right? And I could have a 1 that goes with all of those, correct? I could have a U, a V, a W, an X, but I could have a 2 that goes with all of those, right? I could have a U, a V, a W, an X, or a 3 that goes with all of them. I can do it with a 4. The thing that people struggle with in creating sample spaces is, because if I ask you to just create the sample space and you just say, look, I could get a 1 and a U, I could get a 2 with a V, I get a 6 with an X. If I go about it that way, I'm probably going to leave something out. Does that make sense? So usually the toughest thing is to develop a system or a structure that guarantees we don't leave any combinations out. So that is all my combinations. Okay, I didn't leave anything out, right? Okay, so now, if we look at these, would you agree that those are the 2, that those are less than 3 and a vowel, right? Everything else is either 3 or greater and a vowel or a constant, okay, or consonant. Okay, so now, how many of those do we have? How many favorable outcomes. 2 out of how many total things that could show up? 24. Okay. Now, that's using the sample space, but isn't the formula so much more efficient? And then the idea is, okay, well, what if I ask the question, what if I have like a dodecahedron? You guys know what a dodecahedron is? What's a dodecagon? You guys remember that? A 12. So a dodecagon is a 12-sided polygon. So a dodecahedron is a 12-sided dice. Okay. Well, if I say I want to take a 12-sided dice and find the probability that it lands an even number, and I'm going to spin the spinner, but let's say the spinner is all 26 letters, and I ask you, an even number, and it lands on a vowel. Wouldn't that sample space be much bigger? Sample space would be, think about how we did this sample space. How many numbers are on a dice? 6. Okay. How many letters are on my spinner there? 4. Okay. 6 times 4 gives me 24, right? You guys have you done questions in the past where it says Susie has 3 pairs of pants, 4 t-shirts, and 5 hats? How many different outfits can she make? Okay. That's called the fundamental counting principle, and it basically gives you your number. It gives you your sample space size. Okay. Basically, you just take the number of shirts times the number of shoes times the number of hats, and you get how many outfits. Okay. So here, to determine my sample size, 6 objects for event 1, or 6 possibilities for event 1, 4 possibilities for event 2. Okay. So I get that 24 item sample size. If I was talking about a dodecahedron, so 12 sides, and then the entire alphabet, which would be 26, right? Now my sample space would be 12 times 26, which was 12 times 26, 260, 3, is it 312, 314? 12 times 26, 312, okay? You would have to write out a block of 312 items and then go count which ones have an even number and a vowel with them. Does that make sense? Would that be maybe, it would be something we could do, but would it be tedious and time consuming? Yeah, okay. Or it'd be a lot easier to say, okay, well, these are independent events. Okay, on a dodecahedron, there's going to be 6 even numbers. And if I'm looking for vowels, how many vowels are there? A, E, I, O, U. We're going to count Y? We count Y, that's fine. So we got 6, so we take 6 times 6, it'll be 36. 36 out of 312 then. Okay? If I don't consider Y a vowel, it'd be 30 out of 312. Does that kind of make sense though? Okay, because sometimes, so we deal with sample spaces and the images I showed you yesterday with the rolling the dice, we can use those sample spaces on a small basis, but eventually we do away with trying to determine the sample space, what it looks like specifically, but have that fundamental counting principle to give us at least the size of the sample space so we can use our formulas then to get the probabilities much more efficiently. Is it okay? Okay. So the events that cannot happen at the same time are said to be mutually exclusive events. Events that cannot happen at the same time are said to be mutually exclusive events. Another word that you might see in the end of course exam does this type of stuff with vocabulary. They might refer to these as, come on, disjoint events. Okay. An example of this says, for example, you cannot roll a 2 and a 5 on a number cube at the same time, right? So I tell you, what's the probability? I have a dice. I say, what's the probability of rolling a 2 and a 5 at the same time? Those cannot happen at the same time. Those are mutually exclusive events. Okay? So it says if 2 events A and B are mutually exclusive, then the probability of both occurring is 0, like you said. Okay? So the probability of A or B occurring is the sum of the probability of A occurring and the probability of B occurring. Okay? So if I say, what's the probability of rolling a 2 or a 5? Okay, so how many 2s show up on a dice? 1. How many 5s show up on a dice? 1. So I would take the 1/6 from the 2 and the 1/6 from the 5, and I would add them together. Because now I've just created, when I say or, I've created a larger favorable group that goes in the numerator. Okay? The denominator is still the same sample space. Okay? So what I want you guys to see here, and this is when we say or, because there's a couple rules that go with events that have the word or in them. Okay? So if A and B are mutually exclusive, meaning they cannot happen at the same time, then the probability of A and B is 0, and the probability of A or B is the sum of probability A and the probability B. Okay, but that's if they are mutually exclusive, if they're just joint events. Okay, so we got an example. It says student athletes at a local high school may participate in only one sport each season, right? It's kind of what we do. You know, we've got rules that, you know, depending on like certain scenarios, we've in the past had people that play, you know, kickers play soccer and football sometimes, right? We've had some track stars that were, you know, they were really good at the 400, but they were awesome baseball players, so they would do both. Okay, so we have exceptions to this, but traditionally, most high schools, you play one sport per season, okay? So by the structure of that, you cannot play softball and play soccer during the same season, right? Or you can't play softball and play baseball at the same time, okay? The structure of the rules make these events mutually exclusive. Cannot happen at the same time, okay? So it says, during the fall season, 28% of student athletes play basketball and 24% are on the swim team. So what is the probability that a randomly selected student athlete plays basketball or is on the swim team? Okay? So what we've got here says these are mutually exclusive events. Okay? So the probability of A and B, we know is going to be 0. Okay, A, and maybe we should use, instead of A and B, we should use letters like B and S, okay, for basketball or swim. So we know that they are mutually exclusive because B intersect S, or basketball and swimming, is 0. Can't do it at the same time. So then, when we want to answer the question, what is the probability that a randomly selected student plays basketball or is on the swim team, all we have to do is say that probability of basketball or swim is the probability of basketball plus the probability of swim. Okay? Which is ultimately creating a larger numerator for my probabilities. My favorite is creating a larger favorable outcomes. Okay, so what's the probability of basketball? 28%. What's the probability for swim? So if I add those together, I get 52%. Does that kind of make sense? That's pretty easy. And the idea there, let's say that this 28% came from like 28 out of 100. Let's say the 24 came from another group of 100. Okay, do you see how, because I'm adding fractions that have common denominators, the denominator stays 100, right? But now do I make a larger numerator? I have more favorable objects here to compare to this 100 than I did when I was looking at them as individuals. Okay, so that's why when we see the word or is sums, or the addition. Okay, so in the spring season, 15% of athletes play baseball, 23% are on the track team. What is the probability of an athlete either playing baseball or being on the track team? What do I do there? Add them together. 38%, right? It's pretty easy, right? Okay. Now, what happens is when we have events that are not mutually exclusive. Okay. So these are referred, so the word, and this is what I like I get confused when they say mutually exclusive and not mutually exclusive. Those are usually the comments you see in like a high school geometry textbook. When we go into a stats textbook, they use a lot of times the words joint and disjoint. Joint means together, right? Okay. So in my mind, when it says joint or jointed, that means they can occur at the same time. Okay. Disjoint. Okay. Whenever I put the prefix dis on something, that means that they are not whatever is about to come afterwards. So they are not joint. Okay. So it says some events have overlapping occurrences. It says, for example, if we were asked the probability of choosing a red card or an ace from a standard deck of cards, we'd be asking the following. Okay, so let's kind of, I'm just going to go to the side, and instead of reading that scenario to, let's build this. Now I know, and this is something that a lot of textbooks, a lot of end of course exams, they assume your common knowledge, which is maybe a bad thing to do. Okay, how many of you play some version of cards on a regular basis? Okay, so I'm seeing a few hands. I'm not seeing 15 hands. If I would have asked that question 15 years ago, everybody's hand would have been in the air. Everybody played cards. That's what you did. But now you watch Netflix, play on your phone, that kind of stuff, right? Okay. But even though the things that you guys do in your spare time have changed, the questions that authors ask in a math context to understand probability have not changed. So in the past, they assumed everybody knew that that was a standard deck of cards. Okay, you have what we call suits. Okay, so each shape up there, that first shape, what's that first shape up in that first row? What are those called? Those are your clubs. Okay, the next one down are spades, and the other two are easy, right? Hearts and diamonds. Okay, you have 13 cards across, in each, so those are each called a suit. You have 13 cards in every suit. You have an ace, which is, in most games, is either the low card or the high card, right? Okay, but the way this is set up looks like they're saying that the ace is a 1. And then you've got 3 face cards, jack, queen, and king. Okay, so my question was, what's the probability of an ace or a red card, right? So let's think about this, okay? If we're going off the word or here, it's the probability of an ace plus, because or means plus, right? The probability of red. Okay? So let's go ahead and find the probability that we get an ace. How many aces are there? How many favorable outcomes align with being an ace? 4. So let me do it this way. We'll highlight them. So we get these 4. Out of the total number of 52 cards that we could pick out of, right? We're now going to add to it, so now the probability that's red. Well, how many red cards are there? 26. So there's 52 cards right there. Okay, so that's half of 52, right? So the idea is I would say, okay, plus, 52 is on the bottom, 26 out of 52. But what happened when I highlighted the green and the purple cards? There was overlap here, right? And this is what we were talking about when I wrote it in the notes, that there's overlapping occurrences. And seeing a sample space makes it easy to see that there's overlapping occurrences. The idea here is that these are joint occurrences or joint probabilities, which means that those two red aces, they got counted in these 4. Does that make sense? But those two so they got counted here as aces. So these 2 cards right here, let me just highlight just those two cards that we're talking about, right? That card there and that card there, they both got counted because they were aces. They got counted one time because they're aces right here, right? But did they get counted once here as well because they were red? Okay. So if I were to leave this as 30 over 52, that is an incorrect probability because those two cards, what I am saying is that those two cards are now more likely to be chosen than any other card up there. Does that make sense? Okay. So what we have to do is we have to actually remove one iteration of those cards, meaning since they were counted twice, I need to remove it one time so that they only get counted or calculated in the entire probability once. Does that make sense? Okay. So now I would have 28 out of 52. Okay. So these were disjoint or not mutually exclusive events. And when we have disjoint or not mutually exclusive events, this here, that right there, think about these two cards. How would you verbalize in words what those two cards were? They did end up being duplicates, but weren't they? What were the two criteria that we were using to become part of our probability? They were ace and they were red. Okay? So, if I want the probability of ace or red, it's the probability of ace plus the probability of red minus the probability of ace and red. And that right there is that 2 out of 52. There were two cards that are aces and reds. Does that make sense? So what that does for us is that generates what we call our formula for non-mutually exclusive events. Okay? Like I said, you might see it written as they are joint or jointed events. It says the probability of A or, I'm going to use the word or right now. I'll come back and adjust this for notation in a moment. The probability of A or B, if the events are mutually exclusive, or sorry, non-mutually exclusive, is equal to the probability of A plus the probability of B minus the probability of A and B. And what happens is, because these words of or and I think things are so much easier when we use the word or and, but you will see notation that does this. Okay, and I don't know what the symbol is called, but it looks like a U. Looks like it's so this is intersect, and U is the kind of the flipped version of it. Okay, but the U represents the word or. And that is our rule then for non-mutually exclusive events. And every time that we do a scenario that is a non-mutually exclusive event, the concept, whether it's cards or not, is the same thing that's going on here. We had something that got counted in both categories, ultimately a total of 2 times, and we need to remove that once. Okay, so that's why we have to have that subtraction. You will get at the on the in-course exam on Tuesday, you will get a reference sheet. Let me open up a reference sheet, and I believe there is, I don't remember which one it is, but there's a probability rule at the bottom of it. So they give you this as they call it the addition rule. Okay, probability of A or B happening, and then this would be non-mutually exclusive events. They give it to you in this way because if they are mutually exclusive, this would be 0, and you get A plus probability of A plus probability of B, right? Okay, so, and this is the way my stats textbook does it. It does not give you It doesn't give you both formulas. Okay, the textbook doesn't give you this formula and where'd it go? And this formula. It just gives you this one, okay, and makes you understand that, well, if it's P of A and B, but they are impossible to happen at the same time, then that will ultimately be a 0, and you're left with P of A or B for mutually exclusive events. Okay. So go through some questions. This is, what is the probability of rolling either an even number or a multiple of 3 when rolling a standard number cube? Okay. So we're looking for probability of even or multiple of 3. So I'm going to just say M3 for multiple of 3. Okay. So let's think about this. Okay. Because it's or, I'm going to start with this first. I'm going to say probability of even plus probability of a multiple of 3, and then I'm going to subtract the probability of an even and a multiple of 3. Okay, that's kind of hard to see. All right, so rolling. What's the probability of rolling either an even number or a multiple of 3 when rolling a standard number cube? Okay, so how many numbers are even on your number cube, on your dice? 3. Okay, so 2, 4, and 6, right? So 3 out of 6. Okay, how many are multiples of 3? 2, 3, and 6, right? Okay, are any of those even and a multiple of 3? 6. So it would be 1 of the 6. Okay, so then there's a 2/3 probability that I get an even number or a multiple of 3. Now, think about this. Would that be, because the sample space of rolling a dice is small, I could have, so here are my options in rolling a dice. Can I just go through this and get even or multiple of 3? No, that's even. So I cross it off. That's going to be chosen. That's favorable. There's a multiple of 3. Is that even? Even or multiple of 3? Nope. Even or multiple of 3? Yep. How many did I cross off? 4 out of how many? Reduced to 2/3, right? But if my sample size or sample space is greater than this 6, maybe again I've got, you know, some of your questions I might say you've got a 20-sided dice. Okay, maybe you don't want to draw that picture then of the different objects that could come up or occurrences that could come up. So can we think about it mathematically? Okay. So what is the probability of rolling either an odd number or a number less than 4 when rolling a standard number cube? So probability of odd or less than 4. That would be the probability of odd plus probability of less than 4 minus the probability of odd and less than 4. So how many are odd? 3. How many are less than 4? 3. Okay. Hopefully, a scenario like this can all, like if I add those together, I get 100%, right? And that doesn't make sense that, because of my knowledge of the sample space of a cube, that there's no way that odd or less than 4 is going to make up that's a certainty that when I roll it, I'm going to get an odd or a less than 4, because I could get 6, right? And that's not either of those. So now I need to subtract then the probability of odd and less than 4. So how many are odd and less than 4? 2. 1 and 3, right? Okay. So again, we get 4/6. So it is equally likely to occur a number that is even in a multiple of 3, or even or a multiple of 3 is the same scenario, same ultimate probability as an odd or less than 4. See if I've got an example down here. Let's do this one. Because in a litter of 8 kittens, there are 2 brown females, 1 brown male, 3 spotted females, and 2 spotted males. The kitten is selected at random. What is the probability that the kitten will be female or brown? Okay, because it's or, I'm going to write this. Probability of female plus the probability of brown minus the probability of female and brown, right? Okay. And if I can write that, no matter what, I haven't even determined if these are mutually exclusive or not. Okay. But if I look at this, it says there are 2 brown females, right? That first statement, there are 2 brown females. So these would be jointed, probably these are not mutually exclusive events. Okay. So you will have to remove some probability from there. So what's the probability of being female here? How many cats are female? 5? 5 out of 8. How many are brown? 1 to 3. 2 brown and 1 brown male, right? So 3 brown ones. Okay. What's the probability of being female and brown? 2. So what's that give me? 6/8? That reduced to what, 3/4? All right, these types of questions, I know it's kind of hard to see, and you don't need to write this down right now, but just kind of pay attention. These are hard to visualize because the scenario I just gave you about the cat question or the dice question or even the cards question, you can visualize your sample space. You can put that in front of you. You can have a picture of it. Okay. This question, you cannot do that. Okay. It says New Year's Eve, the probability of a person driving while intoxicated is 0.32, 32% chance. So the probability of a person having a driving accident is 9%. And the probability of a person having a driving accident while intoxicated is 6%. So what is the probability of a person driving while intoxicated or having a driving accident? Okay? So in this situation, you do not know. You cannot put in front of you 52 cards and say, okay, highlight the ones that are red and highlight the ones that are aces and see what the overlap is, right? I can't do that. I can't necessarily see that sample space and whether there's overlap here. So what we're going to do is we're going to target the question. Right here is the question, and that's going to tell me how I need to write my probability events. Probability, okay, says driving while intoxicated. So I'm going to use I for intoxicated, or having an accident. So or an accident would look like that. Does that make sense? Okay. So these things are just raw data, raw statistics that have been calculated, recorded over the years, and we can report them. Now, using those together, we can actually come up with a new scenario. This new scenario that was not being reported. Does that make sense? Okay. Because it's or, it's going to be the probability of being intoxicated plus the probability of getting in an accident minus then the probability of getting in an accident and being intoxicated. Okay. And now, because this is an and statement, and and statements turn into multiplication, and multiplication is commutative, right? So I can say accident and intoxication, or if I want to reverse it and say intoxication and accident. Does that make sense? Okay. What's the probability of being intoxicated? What do they say here? 32%. Add to the probability of getting in an accident. 9%. Okay. So of these 32%, some of them were intoxicated, or sorry, all of them were intoxicated, but some of them didn't get in accidents, right? Or did get in accidents. Does that make sense? Here, all of these 9% got in accidents, but some of them were intoxicated and some of them were not. Does that make sense? So we've got to find that some that were intoxicated and in accidents, right? Is that number reported? Probability of a person having a driving accident while intoxicated, 6%. Okay, so these 6% right here, okay, so 32% drove intoxicated, okay, but of those 32%, 6 of them got in accidents. These 9% got in an accident. Of those 9%, 6% were intoxicated. Does that make sense? Okay. If I do that now, what's that? 32 basically plus 0.03, so 0.35. So there's a 35% chance that a person was intoxicated or in an accident on New Year's Eve. Does that make sense? So you can do these types of things. If we have the data reported, if we have the statistics reported, we can still run through our formulas even if we don't have the sample space laid out in front of us. Okay? You know, I mean, I don't have a collection of all these people that I don't even know how many people there were, right? Was there 100 people? Was it 1,000 people? Was it, you know, this could be data collected over, you know, decades. Okay? So this could be hundreds of thousands of people. Okay? I don't know the sample space, so I don't know my denominators, but I can still, because they're reporting them as percentages, I can still run through this and get that result. Okay? I'm going to try to open up an assignment. Math Excel has been down all day, so I'll send an email out if I'm able to get it open. So be on the lookout for that. You guys can go to lunch.